last unit, if we get through the entirety of this last unit, we're going to cover waves and optics. We're going to get as far through this stuff as we can. It's useful to at least be introduced to this, not because of what you'll do next year, but because of where, if you decide to go into physics in the future, having at least an understanding of the wave nature of a lot of stuff is useful. And it is technically part of the grade 11 curriculum, so we're going to do it. Before we get into the nitty-gritty details about waves and such, a bit of the language that I want to address first is this idea of period and frequency. Hands up if we've heard these words in this kind of context before. Yes? Just yes? In what context, James? In sound. What do you mean? Okay, so frequency you said is measured in hertz. You good? You got anything more than that? Sound also travels as a wave. Yes, you are absolutely correct, sir. So sorry. And earthquakes. What about earthquakes? Waves are also okay. Earthquakes also travel in waves. Yes. I want to focus in on period and frequency. Yes.
Frequency is in a radio channel.
Oh, so, okay. So sometimes it might be a radio channel. Okay. So depending on, I'll zoom this in a little bit so it's easier to see. So depending on what radio station frequency you're looking at, you might get a different station. Okay. Where else do these words period and frequency show up? Say the thing that came to your mind that no one is saying.
I don't know what that is, but frequency can also be, I guess, a mathematical term in a sense as well, or...
What do you mean?
Well, frequency can mean like how periodically something happens.
So is it frequency or period? Because you used the one to define the other.
I'd say period is in a period of time, but frequency is how often something happens.
Okay, so frequency is how often something happens.
So almost as if like the period is a length of time when something happens, and the frequency is how often that one thing happens.
A length of time for something to happen. And these things that happen, there's a requirement for these things. Come on, computer, don't be like that. There's a requirement for these kinds of things. It's not just the length of time for just anything to happen. What is special about the things that happen that we talk about having a period? Yes. No. Well, okay, tell me what a sine and cosine graph. And they go up and then down and then up and then down and then they go up and then they go down and then they go up and then they go down and then they go up and then they go down and then they go up and then they go down. So what are they doing? We'll get there. Yes, that is true. There's the word I was looking for. I don't know why there's a gray bar along the top of every other page, but there is, so I'm sorry about that. But yes, the things that happen must be repetitive. We don't talk about the period for something unless that thing happens again and again and again and again. So, ladies, the reason that we call it a period is because it happens with a pattern every 28 days. Oh, you passed it. It's closer.
Oh, really?
Yeah, it's right there.
Oh.
It's a cycle. It's cyclical in nature. Interestingly enough, gentlemen, you also have a hormonal cycle, a hormonal period. Yours is every 10 days, not every 28 to 30 days. It's there. It doesn't look the same, obviously. You don't bleed every 10 days. But you have hormonal changes too, which is why you might be more irritable and unpredictable every 10 days. but it's there. And we never talk about it because it's not nearly as dramatic, but it's there. Take my psychology class. We'll talk about maybe that. Okay, so this word periodic, an event is periodic if it repeats itself. Waves on a shore, wind moving a tree back and forth, a clock hand moving around in a circle. Other things that show up in math class when you're talking about things that are periodic. Anything that you can, so for those of you who have done Math 12, anything that you can use a sine or cosine graph to model would be considered periodic. So even things like what's the big wheel at the Ferris wheel? Would be yet another example. Tides are periodic, that kind of thing. And we tend to want to be able to predict when another one of these events is going to occur. In order to do this, we want to know how often the thing repeats. To be able to do that, we look at the period for one of these events. Now, the definition here, I've given it to you already. A period is the time for one event to repeat itself. So if a wave crashes on the shore every 5 seconds, the period of that wave is 5 seconds. The period is given the capital letter T. It's related to lowercase t. Lowercase t is time. Capital T in this context is not temperature, it is period, just to make things extra confusing. And it is time divided by the number of events. And that time is typically given in seconds.
An example, period, for example, watching a car race would be the length of time the car needs to make the whole circuit, and the sequence would be the quantity of times the car do a lap.
Assuming it was exactly the same, that would be a good example. Races are a difficult one to talk about because by their very nature they're a little bit repetitive, but they're not perfectly repetitive. But it's a similar idea. That clear? Yes, it's called Newton's cradle. Yeah. Tick, 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 forever. A metronome would be another example, yes. So, well then clearly you're not a musician. So period is the time divided by the number of events. Frequency is related to period. Frequency is generally used when the events repeat very often. Frequency is the number of events per second, so it's exactly the opposite of the period. Frequency, given to us as a little f, is the number of events per second. The units of frequency have already been given to us. I can't remember who gave it, but they said it was hertz, which is abbreviated as Hz. And we use hertz because the other units are a little bit convoluted. Well, no, I shouldn't say convoluted. They have been known to cause some confusion. If you have the number of events per second, then we say that the units of frequency are per seconds, or 1/second, or sometimes it's quoted as being inverse seconds. Those are all the ways that we talk about frequency. But the easiest way to recognize it is just reciprocal seconds is just hertz. So these two are obviously related because one of them is time per events and the other one is events per second or events per time. So the relationship there is this. Your period, big T, is equal to 1 over the frequency, which means that your frequency is also equal to 1 over your period. And that's just basic algebra to move that guy around. So, for example, if you had a tuning fork do we know what tuning forks are? Okay, tuning fork's literally a fork, kind of. The two-pronged fork looks like this. Looks like that. And you smack it against something and it rings. And all of these different tuning forks have different pitches.
Yes.
Some are going to be very high, some are going to be very low. And it's that pitch is actually related to frequency. So the higher the pitch, the higher the frequency of those vibrations. So the lower the pitch, the lower the frequency of these vibrations. So we want to find the period and frequency for this particular tuning fork. So if I wanted the period, big T, that's going to equal what? How do I find the period if period is the time for one event to repeat? Yes.
Well, not time, but tuning fork is vibrating for 30 seconds.
Okay. But I want to find a period, which is the time for one of those events to occur. What is it? Is it 8,000 divided by 30? Is it 30 divided by 8,000? What do I want? Do I want the... So 8,000 divided by 30 would give me the number of vibrations per second. If I divided by 30 by 8, it would give me the length of time per event, which is the one that I want, which is what Naya has said twice now, I think, and I interrupted you both times. So to find the period, remember, it's the time divided by the events, and in this case, the events are the vibrations. So we're going to have 30 seconds divided by 8,000 vibrations. What's the period? How many times, or how long does it take that tuning fork to vibrate back and forth once? Yes, Connor.
3.75 times 10 to the negative 3 seconds.
3.75 times 10 to the what?
Negative
3. Okay, which is going to be the same as 0.00375 seconds. It takes very little time for that thing to vibrate back and forth once. Then, to find the frequency, there's a few ways we could do it. We could either go back to our definition for frequency, which is the events per second, or we can say, well, my frequency is actually equal to 1 over my period. So that's just going to be 1 over 0.00375. So what's my frequency? Yeah. 266.6 repeating hertz. Okay. Does anyone want to know what that sounds like?
Yes.
We just have to wait, apparently, for YouTube to start playing. So this is what the tuning fork would sound like if it was vibrating back and forth with a frequency of 266.6 repeating hertz. This is not a nice sound. It's not the worst sound in the world. But this is what that frequency sounds like. No, it does not. Actually, it has nothing to do with the height of the bigness of the frequency. What you're looking for is, here's a bit of an aside. Every object has its own what's called resonant frequency. And what resonant frequency is, it's the frequency at which it will vibrate perfectly. And so those people who do break glass find the resonant frequency of that glass that causes it to vibrate ever increasingly until the thing explodes. So it's not about the high frequency, it's about finding a resonance frequency. Another example of this has nothing to do with screaming and blowing up glass. Has anyone ever heard of the Tacoma Narrows Bridge?
No.
Her name was Galloping Gertie, and when the wind would blow through the Tacoma Narrows Valley, it would cause the bridge to bend back and forth like this, to the point where one day the thing exploded, and the Tacoma Narrows Bridge is now at the bottom of the Tacoma Narrows. It was speculated at the time that was in part to the wind finding the resonant frequency of that bridge, causing it to
Where did this happen?
explode. Down in Washington State. Tacoma Narrows is just south of Seattle.
Oh, okay, so like, oh, right there.
Yeah. So this is period and frequency. So knowing that we're going to go start moving forward here and talking about waves, waves are things that are repetitive, cyclical, and so having these ideas of period and frequency, even the fact that we're talking about sound already, should kind of give you an idea of where we're going with this. Flip the page. A couple more examples. So if a dog's tail is wagging back and forth 15 times in 12 seconds, what's the period of that? How'd you do it? T equals? Sorry? Time over events. So it's going to be 12 over 15. So that means this dog is wagging its tail back and forth once every 0.8 seconds. Dog's very happy. Often these periods and frequencies do in fact relate to something. What's the frequency? F is going to equal? How'd you do it? Yeah, so frequency is 1 over the period. So it's going to be 1 over 0.8, which is going to give us the 1.25 wags per second. Which means after one wag, how long must you wait for another one? Which one of those things are we going to interpret as after one wag, we must wait how long for the next? The period, which is 0.8 seconds. Cool. So, these aren't difficult concepts. They just might be new to some of you. Another one, a record player spins at 45 revolutions per minute. What is the frequency in hertz? What is the period?
About hertz, I heard about in monitors, about
Yes. So it's the refresh rate. So a computer monitor is something that refreshes itself, and it refreshes itself regularly. 60 times per second.
So it's like gamer ones, like it's 100.
Let's write that down. So we've got computer monitors. If you've got a simple one, maybe a 60 hertz refresh rate. Remember what hertz means. Hertz is per second. So it's something per second. So in this case, a 60 hertz refresh rate is going to be 60 refreshes per second. You're about to say something about a gaming monitor?
I have a friend that has 140 hertz input, and like it played in mine, it's 75, and I can feel the difference.
They're often a lot sharper.
You're getting more information per second.
Yeah. It's smoother, typically, yeah. There is a point at which the human eye can no longer perceive the improvement. I don't remember what that refresh rate is, but it's surprisingly high. Yeah, no, it's surprisingly high. So back to these two, and then we'll talk about radio stations here in a second. A record player spinning at 45 revolutions per minute. What's the frequency in hertz and what's the period? RPMs is, as I've already said here, revolutions per minute. So, but I don't want revs per minute. What do I want to find hertz? I want to take revs per minute, and I want to turn this thing into revs per second. So how do I do that unit conversion? This goes all the way back to the very first unit we did. Yeah, Connor.
Times it by 60.
Do I times it by 60 or do I multiply by 60? Which one? Let's take a look. I have revs per minute, and I want to multiply it by something to give me revs per second. So I'm going to multiply it by this conversion factor. Is minutes going to go on the top or the bottom to convert us from minutes to seconds? It's going to go on the top because minute was on the bottom. If I put it on the top, that means they're going to cancel out. Are you okay? Okay. And so we're going to put seconds on the bottom because that's what we want to replace minutes with. My minutes are going to cancel. That's great. It's going to give me revs per second. Now, what is the conversion from minutes to second? 60 what? 60 seconds in 1 minute. So 1 minute is going to be 60 seconds. So my multiplier dividing by 60. Look at the math here. Am I multiplying or dividing by 60? I'm dividing by 60. So 45 revolutions per minute times 1 minute per 60 seconds is going to give me how many revolutions per second? 0.75 revs per second, which is 0.75 hertz. So the frequency of that record player is very, very low. Then to find the period, wow, it just got very perfumey all of a sudden. Did you use hand sanitizer? Smells good. T is equal to 1 over the frequency. So 1 over 0.75, what's the period going to be? 1.3 repeating, and the units on the period are? It's always measured in seconds. Period is a length of time. Time is measured in seconds. So then, if a frequency of a wave is doubled, what's going to happen to the period? Well, let's take a look at this. I have period equal to 1 over the frequency. If I double my frequency, 1 over 2f, what's that going to do to my period? I call this my new frequency, my new period, t with a little star there, is equal to 1 over 2 times the original frequency. What's that going to do? This goes back to our unit on gravitation where I said, well, what happens if we double the radius? What happens if we double the mass? What happens if we halve the radius? How did we reason our way through what that meant? Does anyone remember? Yes, Connor?
Your period's going to be a lot shorter.
Exactly how much shorter?
Double.
That's longer. Doubling is bigger. Half. There you go. Because what we're going to have here, 1 over frequency is our original period. So this new period, this thing that I call the t with a star next to it, is going to be equal to the old period, 1 over f here, divided by 2. So it's going to be half as long. Which makes sense. If things happen faster, the length of time for them to occur gets shorter. That makes sense, yeah? So at one point, right at the beginning, someone mentioned something about radio stations. What are you talking about when you say radio? How are radio stations related to this idea of frequency? Yeah.
They work on different frequencies.
What does that mean?
It means that you spin a dial or a knob, which will change the radio's its tuner, which I guess gets different waves.
Okay, so we're getting a little bit warmer now all of a sudden. That last word is important. So depending on the radio stations you guys listen to, does anyone here actually listen to the radio? Hands up if you listen to the radio. Manuel, what is the #1 station you listen to? So 95.1. Connor, what's the radio station you listen to? 92.9. Give me some other ones. Emma? 103.5. Used to be QMFM. Yeah, Eric? Okay. Khalil? 104.1. 96.9 Jack FM. I love it. Someone here listens to that. That's fantastic. Who else? What else? Nobody listens to my favorite radio station. That's sad. Sorry? 94.5 used to be known as The Beat back in the day. Don't know if it's still known as The Beat.
AM 980.
AM 980. That's a whole nother beast. Um, you can't actually, in this one we're talking about here, we can't actually talk about AM stations. We can only talk about FM stations.
They must work on the same principle.
They don't actually. That's why they're different. One is AM and one is FM. They work on actually two different principles. 93.7. Country boy over there. Love that. Nobody listens to my 99.3 The Fox. Sad. Okay, so what these things are, these are all, they're related in that they are all FM stations. Does anyone know what that F in FM stands for? If you had to guess, based on where I'm bringing it up, it's frequency.
Just gonna look it up.
And the M stands for, does anyone have a guess?
No.
What are you doing to get from one of these things to the next? If these are all frequencies, an M word that means to change frequency is? Anybody? That's cool. That's fine. Modulation. It was right on the tip of all of your tongues, right? So the FM band of stations is all about frequency modulation. It's changing the frequency. And what you're doing is you're changing the frequency on a receiver to pick up different radio stations.
That's basically what I was saying.
Kind of. But again, lots of things are basically like what you were saying, but they're not exactly the way you were saying. Like, remember we talked about knitting a sweater the other day?
Yeah.
Put the sweater together in your head, and then it's a sweater, as opposed to something that vaguely resembles a sweater. But you were close. The sweater was close. So what's actually happening here? For those of you who might not know, radio stations are a particular kind of wave we're going to talk about in a little bit more detail later on. Short form is they're electromagnetic waves. So they look like this as they travel through the atmosphere. Now, if the frequency for these things, if they have this kind of shape, is, they go just like what James and I were talking about earlier. Put your phone away, James. They go up, and then they go down, and then they go up, and then they go down, and then they go up, and then they go down. So the event that we're talking about here when we talk about frequency, because frequency is the number of events per second. So if the radio station you're listening to is 94.5, what that means is what that radio wave is doing is it's going up and down 94.5 times every second. So maybe you don't want to listen to something that's going up and down 94.5 times per second. Maybe you want to tune it so you're listening to something that goes up and down 93.7 times per second. Now all of a sudden you're listening to country somehow. And so we get all of these different radio stations are assigned a particular slot in this radio band of frequencies so that they get, every one of them is a wave that is specifically shaped to be received by a specifically shaped tuner. So, which is why sometimes as you travel from one city to another, it's worse in the States where things are more closely packed together. You can listen to the same frequency and all of a sudden you get two radio stations talking over top of each other. Because these frequency bands have been assigned to different stations in different cities, and your receiver is close enough to both of them to pick them up, and they interfere with each other. But it's these radio waves going up and down. That is what these numbers represent. Yeah.
Does that mean when it's going 96.9 or whatever times per second, like up and down?
Yeah.
Does that mean the speed in which we hear them will change, or is it so small that we wouldn't notice?
I will in the next little lesson here, I'll introduce how speed is related to all of this. No, and the short answer is no. The speed for, especially for these electromagnetic waves, all electromagnetic waves, regardless of frequency, travel at the speed of light.
Nice.
Which is on your formula sheet, but it's almost 3 times 10 to the 8 meters per second. Very fast. Yes, sir?
Would there be like a difference between sound quality?
Not necessarily. That's all dependent on the rest of your sound system. Yeah, you bet. So this is where these ideas of waves, they're applicable all over the place. And this is kind of where we're going to go. We're going to focus on EM waves, so light and radio. Wow, that is quite the laugh. And we're going to focus on sound and water waves as well. So we're going to spend the next couple lessons looking at each one of these specifically. If we have time, we're going to do a deep dive into light and look at optics and lenses and mirrors and that kind of thing and how light behaves. But that is only if we have enough time. So what I want you to do, take a couple minutes now, because I think there's just over, well, he's just under, it's more than 20 minutes. Well, it's 19 minutes from 1 o'clock, so we've got almost half an hour. I do want you to flip this over. Take a look at some of these. Thank you. Let's do evens. Giver. There's the computer screen thing.
I added up. I'm not done on my videos yet, but I've added them up and my presentation.
There we go, unpause. So mechanical waves and electromagnetic waves. This is the first kind of distinction I want to make here between waves. Mechanical waves require a medium. So any wave that requires a medium to travel through is what we call a mechanical wave. Things actually have to be moving up and down or back and forth. So examples of mechanical waves are things like sound. You take out the air, you take out the water, wherever the sound is originating, that sound will not propagate, is the language we use here for passing on. Ocean waves. I think that one goes without saying. All of a sudden the water is gone. Now you don't have waves for the ocean waves to travel through. There's no ocean, so there's no waves. That's a really simple example. So these are all, that is the definition of a mechanical wave. Electromagnetic, yes sir?
Isn't the desert where all the pyramids are, didn't that used to be covered by water?
This whole planet at one point was covered by water. Anyway, let's carry on with this. Not related at all. You know what? Actually, the bell's going to go here in less than a minute, so this is where we'll pause. Welcome to Waves.